So I'm Shafi Goldwasser, and I'm the director of the Weizmann Institute for the Theory of Computing and UC Berkeley. And this summer at the Weizmann Institute, we've been experimenting with a new format of summer activities. We are running summer clusters, which are focused research efforts on various topics in computer science and in the theory of computer science. And by focused research efforts, I mean we invite a smaller group than a large-scale program to come to the Weizmann Institute and to study problems of interest and of importance in a sustained and focused manner for a period of 2 weeks to 6 to 8 weeks in the summertime. And we were very fortunate to run 2 of these clusters this summer. One of them was a cluster on quantum computation, and one of them was a mini cluster, a much shorter one, for 2 weeks on algorithmic fairness. And today we have with us Umesh Vazirani, Guy Rothblum, and Cynthia Dwork. Hi. Hi. Thank you very much, Umesh, Guy, and Cynthia, for coming for an interview to find out what the clusters were about, and more importantly, what your fields are about. What is quantum computation about today? What are the most important questions? And similarly, for algorithmic fairness. I think I'll start with Umesh. Start from left. We'll randomize the order. But hi, Umesh.
Hi.
And we all know that the topic of quantum computation has been taking more and more center stage. There's very interesting efforts in universities and in research laboratories and in countries toward building a quantum computer. And in recent years, there's been success, actually, in being able to utilize more and more quantum beats in a controlled fashion. And my question to you is, what is the role of computer science in this development? And please.
Yeah, that's a great question. Actually, in a certain sense, this recent success on the experimental side in quantum computing, it's that's come about both in industry and in academia, and with a great deal of effort and ingenuity on the part of experimentalists, in terms of pushing the boundaries. But together with that, what's become clear is that the major challenge moving forward is algorithmic. So what are we going to do with these near-term quantum computers once they are built? And how will we even test that they are quantum? So it turns out that this is sort of a widely acknowledged at this point. It's an increasingly and widely acknowledged challenge, which is how do we get computer scientists engaged in this enterprise on a much larger scale? And that was one of the issues that we had in mind in running this summer cluster, which was to actually focus in on these algorithmic challenges. And in order to focus it, in order to understand these challenges, actually you have to have a deep engagement between computer scientists and quantum chemists and physicists. And it's the sort of engagement that you cannot carry out. You cannot ask the computer scientists to go to physics conferences or chemistry conferences, because that just would not be a place where you can actually understand the computational issues. And so this is where the Weizmann Institute really occupies a unique place, where it provides this kind of playground where we can actually have this engagement at a deep level between chemists and physicists and computer scientists while actually focusing much more on the computational side and the algorithmic side of these problems.
So it's very interesting what you're saying. So you're saying there are these large-scale efforts, and in fact they involve many people and a lot of funding to build these computers, but we don't really know yet what to do with them, even once they would be built. And this is a place where algorithm designers, computer scientists, have a crucial role to play.
That's right. The issue that comes up in the near term is, so we have a much better understanding of what you could do in the long term with quantum computers. but in the near term, quantum computers are going to be much more noisy, and they'll be smaller scale, and in that regime we have much less understanding of the algorithmic capabilities of these computers. So in a sense, what's happened now is we should sort of contrast and compare where we are today to the very early days of quantum computing, which just about 25 years ago, when the early steps in quantum computing were all taken, through quantum complexity theory and quantum algorithms. So computer scientists sort of developed and understood that this was a wonderful new field, and then there was this challenge of bringing the physicists up to speed on this subject. And in fact, what happened is that over a sequence of years, we had these summer workshops at Villa Guardino in Torino, in Italy. So this was a villa on the top of the hill in Torino. It was devoted to a foundation. There was a foundation called the ISI, the Institute for Scientific Interchange, which wanted to promote new science, and basically it was a place where computer scientists and physicists hung out together for about 6 weeks every summer, and over the course of these interactions, we developed the language of quantum computing, and it was a really exciting time. It was a playground, to develop this sort of interdisciplinary, collaboration, and in a sense, where we are today is an echo of where we were 25 years ago, except now, this time, what we are trying to do is, now the experimental physicists have managed to reach much farther, make a lot of progress in terms of where they are, and but now we have completely new algorithmic challenges. And in order to even understand what those challenges are, and in order to sort of abstract out and the correct questions and the correct paradigms, we really have to have an interaction, at a deep level. And once the most interesting thing is when you're in this kind of interdisciplinary sort of regime, reading papers by the other group, this is not really practical. It takes a very long time. It's very hard to interpret those papers, and it's much easier if you set up the right kind of workshops, with the right format, so that you actually make sure that discussion is given primacy over just presentation. And so this is what we really tried to do in this 8-week program. So we had it was very stimulating and very very successful.
So one of the things you brought up is that there are new algorithmic challenges, and from what I gather, one of the algorithmic challenges, how do you verify actually? You referred to it in your first answer. How do you verify that the quantum computer is actually doing something beyond what a classical computer would do?
Yeah.
So can you tell us a little bit about that?
Yes. That's it's sort of a unique challenge in the sense that a quantum computer is at the same time an incredibly powerful object, in the sense that it can compute exponentially faster, or do computations which are prohibitively hard classically. It also covers its tracks extremely well. So in other words, if you try to peek inside a quantum computer, its quantum state collapses, and all you see is a small classical state. And so it's very hard to check something if it keeps covering its tracks. And the covering of the tracks is is really a part of the axioms of quantum mechanics. So it's built into quantum mechanics. And so, one of the recent breakthroughs is understanding how to, to think about to think about this quantum computer as something whose power we can limit by using cryptography. And this is a very interesting notion that, to say, well, even though this quantum computer is extremely powerful, there are certain things it cannot do well, and these involve certain, that there are certain classical tasks which even a quantum computer cannot perform. And then how can we use these classical tasks as leverage to check that the quantum computer is doing what it's supposed to be doing? And so, there's this real interesting leverage that you get by taking something it can't do to check that it's doing everything else it's supposed to be doing.
So to paraphrase, it's sort of coming from the point of view of sort of thinking about it. So to paraphrase, we're thinking here of a proof as an adversarial process. So there is this quantum computer or someone who built a quantum computer that claims that there are certain computations that have been done. And you're suspicious of these claims.
Yeah.
And any proof is in some sense verifying some suspicious claim. And how do you verify the suspicious claim? So you're sort of viewing the claimer as an adversary, and you say, well, he's an adversary. There's certain things this adversary can't do. Yeah. And if I somehow combine the challenges of what he claims to do with the challenges which he can't do in such a way that he can only answer truthfully, because otherwise he would solve this difficult challenge.
Yes.
So I assume that that's something along those
yes,
lines.
and so that's exactly right. It's in that sense, this testing of quantum computers actually ties up in a very deep way to both cryptography and complexity theory, where these interactive proof systems, where you're interacting with a powerful prover. In complexity theory, the powerful prover is a mythical powerful prover, but in quantum computation, this powerful prover is your quantum computer. So it's really, at the same time it's a very deep connection, but it's also a very practical connection as we are discovering. And so this is another sense in which the Simons Institute is really acting as a playground where quantum computation is interacting with cryptography and complexity theory, more classical complexity theory and classical cryptography, again to bring people together where they don't have to necessarily learn everything about the other field while tackling some of these central questions.
So in fact, I think that in this workshop that you ran a workshop as part of your cluster. There were a lot of cryptographers who participated, and they were extremely excited. They're saying there's this exciting things happening in quantum computers where they're using cryptography, and we now want to learn much more about quantum computers than ever before, because you could see that their own field is being used.
Yes. I should focus on two talks in particular. There was a talk by Yael Kalai where she spoke about how some concepts from quantum computing, no signaling, were used in cryptography. And then there was a talk by my own student, Urmila Mahadev, who spoke about how post-quantum cryptography, concepts from cryptography could be used to test quantum computers. And it was really an exciting session, and it was one where as you said, there was a great deal of excitement on the part of cryptographers to learn about these new connections.
Right. Particularly using, I think, the learning with error problem which
Yes.
is right now hard, or what we call quantum resilient, as the basis, as this hard computational problem that we assume the quantum computers can't solve, and this work that you referred to of your student, she leverages this impossibility in order to verify,
Yes.
right, the correctness. It's
That's
very,
right.
it's very
It's
exciting.
really beautiful work, and it's really exciting.
Yeah. Wow, I want to learn more as a cryptographer. And I agree with you that I think that part of the mission of the Simons Institute is to enable this kind of collaboration between people from other disciplines, but even within theoretical computer science. You know, people who work on quantum computing versus cryptography versus complexity, to establish a common language, and also to realize that we need these common skills in order to make meaningful contributions.
Yeah, one of the ways I think about it is that that if well, I usually think of this as viscosity. You know, when each of our fields has some. You know, if you try to understand something in even a neighboring field, and you try to read the papers, it's just so viscous. It's so hard to move through them, and whereas if you have the people who wrote those papers next to you, the actual ideas and concepts are so much easier than what actually gets conveyed through the papers, and so it takes a place like this, like the Simons Institute. One could imagine that it really speeds up the process of scientific discovery by an order of magnitude or two, because it's just so much faster and so much more efficient.
Thank you, Umesh. Now I want to turn to the fairness cluster. It's all the rage. I mean, it's kind of amazing how quickly this idea of using algorithms in terms, or sometimes people think of it as just machine learning, but algorithms to make decisions that previously were made by humans, people who have been trained to do so, in the judicial system, in policing, in many other areas of life. There's discussion about replacing existing mechanisms by algorithms. And I understand that a very important question is how you ensure that these algorithms work in a fair manner. But I have a much lesser understanding of what it means to be fair, and I think that this question is it's a difficult question, right? What does it mean to be fair? And my first question is sort of how do you see the role of algorithmic fairness in the context of computer science, or what is algorithmic fairness?
Great. Okay. So the air quotes that you put in were very apt, because in many ways we really don't know. So you mentioned many areas in which algorithms are starting to make decisions that previously had been made by humans and by trained humans. But one area in which algorithms have been making decisions all along has been online advertising. And so when we started thinking about this work back in 2010, there were already plenty of online systems and ad platforms that were doing exactly this. So the Wall Street Journal actually ran a really interesting series of articles called What They Know, which was mostly about privacy. But they did raise a particular scenario. So at the time that the article was written, in August of 2010, if you went to a bank website, before the bank would actually show you anything, it would consult with a tracking network, and the tracking network would already have placed you into some tens or dozens of demographic bins. And based on your bin, and only on your bin, you would be shown a certain ad. And so the concern that was raised in that article was the worry about the illegal practice of steering minorities to credit card offerings of less desirable terms. So the credit industry is more tightly regulated than other industries, many other industries in this country, and even in the advertisements in the online world, there are regulations that were relevant. So in that sort of a setting, you kind of imagine that you have a population. Your population has various demographic minorities. It could be racial minorities, gender preference minorities, medical minorities, people with various sorts of disabilities, religious minorities, political minorities, and so on. And so you might be thinking in terms of somehow trying to find notions of fairness that treated groups the same way. And when we started working on this, we, started in that general approach. But we also, having some background in cryptography, started thinking, as you said, we were thinking about adversarial advertisers. What would they want? And we started listing all of the goals of the adversary. And then when we thought about very natural notions of group fairness, we realized that they wouldn't defeat some of these adversarial goals. And so we knew that we suspected that group notions were just not good solution concepts for fairness. And started turning to a notion of individual fairness. So individual fairness would say, roughly speaking, that if two people are very similar for a specific classification task, then they ought to be treated similarly. And
this is really tied to a classification task. For each classification task, there could be different similarity measures.
Exactly. And you and I might be very similar for some things and completely different for, say, movie recommendations or whatever. So that sort of brings up the general paradigm that you pioneered, which is when you're trying to handle a kind of big question, you have to first of all define what are the goals of the adversary and therefore what does it mean to get it right. And then once you've got some definitions, you try to find some algorithms that satisfy these definitions. And finally, because as we see, people are classified over and over and over again in many different contexts, we want to understand something about how things behave under composition. So that's a general framework for trying to make some progress here. As we've been discussing, the definitions are difficult, and they present challenges that I haven't seen before in cryptography, in privacy, just completely different sorts of challenges. And one of the reasons is that fairness is fundamentally, it's a question of sort of human and emotional perception, and the process of arriving at something that's considered fair is a fundamentally political process. But politicians can say things that are sort of stupid and that have silly consequences. So computer science...
We'll definitely have that. Okay.
So computer science has a real role here in sort of saying, what do you mean by fairness? If you're going to legislate some sort of fairness, what does it mean? And what are the consequences of anything that you might say? So we have these group fairness definitions, which we don't like for the reasons we described. We have these individual fairness definitions, which are really nice and have really pleasing math, but this notion of how similar or dissimilar people are for a particular classification task, where does that metric come from? We don't know. We don't know how to find it. So now there's some movement to finding definitions that kind of bridge these two general principles.
So I know that one of the definitions that it's most appealing to me is this idea that maybe you can define what fairness is, but what's behind it is when people say something's not fair, it's not because when they like to complain, although that's itself a holy goal, but it's because they want to change the outcome. So rather than actually defining fairness, you want to make it such that you could change the outcome.
Right.
And that's a very interesting way that I think that you are working on now, to come up with a definition. And just going back to cryptography, sort of related to your non-malleable
So in fact, in some cases, malleability here might be a good thing.
Exactly, it's exactly the opposite, but malleability is the issue. It's not so much can you learn about a message from its encryption, but can you essentially come up with another encryption whose underlying message is related to something that was sent in the past. So here you actually want things to be malleable in some sense, right?
You might. So if somebody is, say, applying for a loan and they're turned down, when they say, why was I turned down, you might think that the real question is, what can I do at reasonable cost that will get to a different outcome, get to the other outcome? So we're calling this concept negotiability for now. And there are all sorts of really natural questions that you could sort of start going into the cryptographic framework and obfuscation and blah blah blah. But negotiability, it seems really appealing. Of course, there are worries about if you have a negotiable classifier, it'll be gameable, and how do you make sure that that's not what's going on. Also, there seem to be some kinds of connections to kind of the adversarial learning, where adding a little bit of noise can completely change the classification. And it's a bad thing there, but it might be good here.
Right, it's exactly opposing goals, seemingly. Yeah.
Exactly.
So the question is how to make sure that it's not opposing.
Right, and then there's other work done recently on explanation. So you have a machine learning system that, say, reads an X-ray and decides that something is cancer, and provides an explanation which is pointing to a certain collection of pixels and saying because of these pixels. Mm-hmm. And it turns out that you can just perturb the image a bit and keep the same classification, but the explanation turns out to be completely brittle. Mm-hmm. And so for us, that would correspond to saying, well, here are completely different things that you could do to come to a different outcome. In our case, it's not bad. It's not a bad thing. But anyway, we're trying to understand how all of these things are connected to each other.
So let me move to you, Guy. Cynthia mentioned the question of composition. That part of the challenge is that you want to be able to compose different fairness, and how do you do it if you use different definitions, maybe being members of different groups. And I know that you have some work on composition. Maybe you want to tell us a little bit about that?
So I want to speak about that, and I generally want to speak about what we as computer scientists can bring to the table in talking about fairness. And we should say that fairness really is, it's a big question. It's multidisciplinary. I mean, it spans social sciences, economics, ethics, law. And when we as computer science come to talk about fairness, we of course are ambitious and we want to solve as much of it as we can, but we know that it's a big problem. And we try to tackle it as computer scientists, to abstract it to the best of our ability and to tackle pieces of it. Cynthia was speaking about the great difficulty of arriving at a single sort of all-spanning definition of fairness. I think that's a real difficulty, and part of the work we've been doing, or the community has been engaged in, is getting there, proposing different notions of fairness. And coming from the cryptographic background, also trying to define particular concerns about fairness. So it might be very difficult to define in a single, concise way what fairness is, but it might also be much easier to define various notions of unfairness, as Cynthia was mentioning that she did in her early work. And so as cryptographers, one thing that we could think of is trying to model different fairness concerns and maybe fight, propose a method for fighting fairness concern 1 and fairness concern 2, fairness concern 3, and hopefully this sort of is a path towards progress. And maybe at the end of the day we'll reach a single all-spanning definition of fairness and show how to guarantee it. Maybe we'll have this sort of quiver full of arrows that we can use to combat different types of discrimination. And so along these lines, one work that I've been engaged in recently, again, thinking about fairness from a computer science perspective, one thing we could try to do is to combat all the ills that already exist in the world, but another is trying to identify, what kinds of unfairnesses might computer science itself be generating, and how can we fight those? This isn't a new concern. I think it's been receiving a lot of popular attention, but if we use algorithms to make decisions, the decisions might be biased because the algorithms are trained on biased data, and that's bad. But another concern is even if the data themselves aren't biased, the algorithms could be introducing bias and discrimination. For example, because classifying a certain minority is computationally expensive. Okay, so maybe the minority finding, say, qualified loan applicants in a minority, there are plenty of them, but they look different from the ones in the majority. And the algorithm, if we just unleash it into the wild, let it run on its own, would optimize really well on part of the population and ignore the other part. So this is a discrimination that isn't in the data, but is sort of introduced because of computational considerations. And that may well be something we want to fight. And so we have definitions talking about, we call this multi-calibration, sort of ensuring that the algorithm does pay attention to all of the different subpopulations that might be present, whether it's minorities, whether we're talking about different types of minorities and intersectionality, and trying to sort of use the power of computer science to combat this concern. So sort of computer science to fix it and really make sure that the algorithm is paying attention to all of the different populations that it should be and not ignoring them. So that's work that happened in the past. One of the things we've been engaged in over the summer that I think is very exciting is taking this line of work and together with, we've been engaged in this with Cynthia, taking this line of work and applying it not only to making sure that the data about all the different populations is represented in the result, but also using these insights, moving them forward to doing some sort of affirmative action. So correcting for biases that are in the data. Not just representing truth as it is in the data, but hopefully representing sort of truth as we would want it to be.
So in some sense you're saying, on one hand, we want to make sure that we're not doing harm by using algorithms, but we can actually use algorithms to detect biases that exist. And to kind of give, it's one thing to talk about biases, but we can give support to it because we can show algorithmically outcomes that are in some sense proof to the fact that there is bias in the existing data.
Mm-hmm. Yeah. And then we can use algorithmic techniques to correct for it.
Right. So I have a question about how, I know you had a very small cluster and the hope is to have a larger one in the future. It was 2 weeks, right?
It was 2 weeks.
What was it like?
It was
to be here for
fabulous.
2 weeks?
It was fabulous. It was very, very intense. And there's been a real explosion of research in the theoretical computer science community and also in the machine learning community, sort of NIPS and ICML sorts of communities.
On this topic?
On fairness, on algorithmic fairness. And even in the last 2 to 3 years, just a tremendous number of papers. So we had a number of people who have been doing some of this work together to, sort of like what you were saying, everybody could read each other's papers, but a lot of headway was made when we could just really stop people and say, explain this point, explain this point. And we made a lot of progress.
That's great.
And really developed, I think, several new lines of research, and this was only in 2 weeks. It's taking a lot of time just to sort of process what we experienced.
Absolutely.
So many things came out of it. And one of the really, really nice bonuses, we had a talk from Lucia Jacobs, who's in the psychology department
At Berkeley.
Came and gave us a talk on the anthropology of fairness. And it was absolutely fascinating. It was objectively fascinating, but it also suggested that there might be some very sort of few principles on which, at least anthropologically, fairness seemed to be based. It doesn't mean that it's right for what we're doing now in the online world and so on, but it was very suggestive this way. And Lucia will be visiting Radcliffe as a Radcliffe Fellow next year, and she and I already have some experiments planned involving squirrels.
Can you tell us, like, if you had to take one nugget from the idea of anthropological fairness, what would you say? I think some people would say that life is not fair, growing up in a Jewish family, and that you just have to deal with it. But what is something that you think evolutionary is an example
I'll
of
tell you
fairness?
something that surprised me that she mentioned that I hadn't thought of.
Okay.
So she was talking about the size of food packets. So if you manage to get a small rabbit, that's a small food packet. If you manage to kill an elephant, that's a very large food packet. And she talked about things like that the cost of defending a large food packet, once you have eaten enough, is too high. And so you share it, but you also get status by sharing. And so the talk was filled with these little nuggets like that. And I don't know, I think you had some take-home messages. Do you remember?
I do. So one thing was certainly, there, as Cynthia was saying, there are these simple facts or principles about the environment that really affect people's perceptions of fairness. So, for example, in a society where food is scarce, perhaps people are less willing to share. As Cynthia was saying, in a society where food packets are very large, for example, there was one example of villagers on islands in Indonesia that hunt whales. So the hunting is a collaborative effort, sort of by its very nature. It's very difficult for one person to bring down a whale, and even if one person brings down a whale, it's not clear what they would do with the whale. So, there's seem to be very evolved protocols for how one shares in the spoils, what rewards each person who did a certain task gets after the whale is brought down, and then there are experiments of how these people feel about how people in this sort of environment feel about certain divisions of goods or certain offers and ways of dividing goods, what is fair and what isn't fair, and it's very different from environments where food is scarce or it's every man every person for themselves. So it's a simple example of how the environment can really affect a community's perception of fairness.
So it would be wonderful if there were simple principles that one could derive definition of fairness from, sort of like in the physics way, right? So they're sort of laws of fairness, and they don't involve, that what goes up, something goes up, then something else goes down. That's always what's fascinating about physics, that they're sort of simple rules, and they're not elaborate definitions.
So that's one of the thoughts, that maybe individual fairness, that similar should be treated similarly, would be such an example. And there's a really famous video that you can find on YouTube of a pair of capuchin monkeys and an experiment. The monkeys have to carry out a task. In this case, it's to hand a rock to the experimenters, and the monkeys are rewarded with some food. So in this experiment, you've got a pair of monkeys, and the first monkey hands the rock over and gets a slice of cucumber and is perfectly happy with the cucumber. The second monkey does the same task and gets a grape. And then the first monkey does this task again and gets a cucumber. But the first monkey has seen the grape and seen the other one get a grape. And when it gets the cucumber, it goes ballistic. And first it just throws it back at the experimenter. And then it sticks its arm out of the cage and starts pounding the table. And it jumps up and down and so on. It doesn't want a cucumber when the other one got a grape.
So it's really about what the other one got.
Well, that's what I took from it. But actually, I'm not sure. And here's the question that I have and that Lucia and I want to experiment with. Suppose you started with feeding this monkey, just one monkey, and you give it a cucumber. And then the next time you reward it, same one, with a grape. Mm-hmm. And then the third time you reward it with a cucumber. Is it going to say, wait,
I want a grape.
Grapes are possible. And maybe that's what it learned by seeing its friend get a grape. It's just that grapes are possible, and to hell with this cucumber nonsense. So I don't know. I don't know whether it's the failure of an anticipated reward, which is something that Lucia mentioned in a totally different context, or whether it's the neighbor got the grape. So I want to find out.
I'll add to that it might not be that we can find simple rules that apply to everyone. But one thing that was suggested by this talk is that maybe fairness really, there is no single answer for fairness, but the complexity of the different answers that we might have isn't so great. It's affected by a few variables, things like the packet size or scarcity of food in the environment. So it's not this huge intractable problem, but rather we can simplify it into sort of a few different types of fairness preferences that people have, and then going back to questions about composition, how do we make sure everyone is happy and everyone is getting things that they think are fair? What different people think is fair might be different.
So you brought the example of the talk, and in general I think that social scientists and so forth, and anthropologists in this case, lawyers have thought about these questions of fairness. And all of a sudden we arrive on the scene, we as computer scientists. And one may say that maybe we are presumptuous in thinking that we can advance the field. I personally don't believe it, but I was wondering what your thoughts are on that.
So no, I don't think that we're presumptuous. I think that we're going to have machines making decisions. We have to understand how to instruct them. And the lawyers and the ethicists don't know how. But the other thing is that you can go back to questions in, say, US law on fairness and sorry, I'm forgetting a term. It's a term involving impact? Disparate impact. Okay, so you go on, look at questions on disparate impact, and when you examine them carefully in the context of machine learning, you can see that some of the tests in American law don't make as much sense anymore. So I've been working on developing a project for a bunch of undergraduates to look at this, but I'm working with a graduate student at Harvard in the government department. And he had a lot of insights into how computer science will actually change some basic considerations, and that previous looks at what was going on in the disparate impact case don't actually make sense anymore.
Thank you very much for coming to Simons for this incredible interview. Thanks a lot.
Thank you, Shafi.
Thank you, Shafi.